For centuries, humanity has looked up at the night sky and wondered what lies beyond the countless stars scattered across the darkness. Each new generation has built better telescopes to answer that question, revealing planets, galaxies, and distant cosmic structures once beyond imagination. Yet despite all these discoveries, scientists have come to understand that everything we can see, stars, planets, gas, and dust, makes up only a small fraction of the universe. Most of the cosmos appears to be invisible, hidden from direct observation but influencing everything through gravity and cosmic expansion. Understanding this mysterious, dark universe has become one of the greatest scientific challenges in modern astronomy, and it is the reason the Euclid Space Telescope was built. Euclid is one of the most advanced survey telescopes ever created, designed by thousands of scientists, engineers, and organizations around the world to map the invisible parts of the universe. Unlike traditional telescopes that focus on small regions of space, Euclid combines an incredibly wide field of view with exceptional detail. It can observe vast areas of the sky while still detecting extremely faint galaxies billions of light-years away. This unique capability allows researchers to study how galaxies are organized throughout the universe and how invisible forces have shaped their evolution over billions of years. Its mission is not simply to take beautiful pictures, but to answer one of the biggest questions in science. What is the hidden matter and energy that control the structure and future of the universe? To understand why Euclid matters so much, it helps to look back at one of astronomy's greatest discoveries. Just over a century ago, scientists held a much simpler picture of the cosmos. Many believed the Milky Way represented the entire universe and that the faint, cloudy smudges visible through telescopes were simply part of our own galaxy. Although some astronomers suggested these smudges might actually be separate galaxies, there was no convincing proof. That changed in the early 1920s, when American astronomer Edwin Hubble carefully studied one of these mysterious objects, now known as the Andromeda Galaxy. Hubble focused on a special type of star called a Cepheid variable. These stars brighten and dim regularly over time, and astronomers had already discovered that the rhythm of those changes revealed how bright the stars truly were. By comparing a star's true brightness with how bright it appeared from Earth, Hubble calculated its distance. His measurements showed that the stars within Andromeda were far beyond the boundaries of the Milky Way. This remarkable discovery proved that our galaxy was just one among countless others scattered throughout the universe, dramatically expanding humanity's understanding of space. Soon after this breakthrough, Hubble made another astonishing observation. Examining light coming from distant galaxies, he found that they were moving away from us. Using the Doppler effect, astronomers could determine whether an object was approaching or receding by studying changes in its light. Hubble found that nearly all distant galaxies were moving away, suggesting that the universe itself was expanding rather than staying fixed. This completely changed scientific thinking. Instead of existing forever in a steady state, the universe appeared dynamic and constantly growing. The idea of an expanding universe was hard for many scientists to accept, including Albert Einstein. When Einstein developed his theory of general relativity, he believed the universe was static. To make his equations fit that belief, he introduced an extra mathematical term called the cosmological constant, meant to balance gravity and keep the universe stable. However, once Hubble's observations confirmed that galaxies were moving farther and farther apart, the need for this adjustment seemed to disappear. Scientific attention shifted toward understanding why the universe was expanding and what that meant for its origin. These discoveries eventually led to the development of the Big Bang theory, which proposed that the universe began in a much smaller, hotter, denser state before expanding over billions of years. As astronomers continued observing distant galaxies, they discovered another mystery. Galaxies weren't simply moving away from one another, they were accelerating as they separated. Something seemed to be pushing the universe to expand faster over time. Since acceleration requires energy, scientists searched for a source powerful enough to drive this enormous cosmic change. No visible object could explain it, leading researchers to propose the existence of a completely unknown form of energy spread throughout space. This mysterious force became known as dark energy. At the same time, another puzzle emerged. When scientists calculated the amount of ordinary matter in the universe, including stars, planets, gas, and dust, they found it accounted for only about 5% of everything that exists. The remaining 95% appeared to consist of invisible substances that couldn't be observed directly. About 27% was believed to be dark matter, an invisible form of matter whose gravity helps hold galaxies together and influences the development of large cosmic structures. The remaining 68% was attributed to dark energy, the mysterious force responsible for the universe's accelerating expansion. Although neither dark matter nor dark energy has been directly detected, their effects show up throughout the cosmos and align with many astronomical observations. Scientists have proposed several explanations for dark energy. Some suggest that Einstein's cosmological constant might actually describe the energy contained within empty space itself. Others believe that small quantum particles that briefly appear and disappear throughout space could contribute to this energy, though calculations based on this idea produce results that are far too large. Another possibility is that an unknown field, sometimes called quintessence, acts as a new force spread across the universe. Each explanation has strengths and weaknesses, but none has yet provided a complete answer. Much more evidence is needed before scientists can determine which, if any, of these ideas is correct.